All right, hi everybody. So today we're talking about air drag. Chapter 6 is kind of a hodgepodge of a lot of topics. We're going to talk about drag, centripetal force, and then we'll talk about integration, which is like a backwards derivative. It's actually sometimes called an antiderivative. So let's get started. First, we have two models for drag, right? We have type 1 and type 2, very similar to what we had for projectile motion. However, this time they are sorted by their medium. Type 1 has to do with a viscous medium. Viscous just means it's a thicker medium. This is reserved for mostly fluids or anything that's fluid-like. And type 2 is reserved for air drag. Now, type 1, usually we will deal with water or some thick oil, and you are given what do they call it? So you're given the variables for this given oil, right? In a physics problem. But in air, then you have to solve given a various density, and then we will give you the profile area and things like that. But we'll talk about that in a minute. But they are sorted by their medium, right? Now, typical speed. Typically, you are moving either slowly or quickly in these scenarios. When you travel through water, and this isn't just like on a boat, right, where you're basically just skipping or sliding on top. This is where you're completely submerged, moving in. This medium is usually what we're dealing with in these problems. You're usually moving pretty slow. Then in type 2, for air drag, you're usually moving rather quickly, especially when we start talking about terminal velocity. So the equations here, all right, we have two very different equations. Okay, the first equation for type 1, okay, this is just the general equation. We have R equals BV. That B is going to be a hodgepodge of a lot of different concepts kind of rolled up into one. But then for type 2, for air drag, we have a lot of variables split up because these variables can change drastically. So R equals BV is what we use for viscous fluids, but for air drag, we use 1/2 rho V squared dA. We'll go over what each of those variables mean on the next slide. Now, what we want to do is look at terminal velocity. So equation at terminal velocity. Terminal velocity is when you are falling through a medium, whether it be viscous or fluid, and you are falling and you have accelerated to the maximum speed, and you can no longer fall any faster. This happens while skydiving. We have this picture over here, right, of a man skydiving. When you're skydiving, you can usually reach your terminal velocity and then cruise at that velocity down to the earth and then pull your parachute. Now, this guy also has a board that allows you to move through the air very differently than if you were just gliding without a board. There's also the flying squirrel suits that also give you a lot more control of your mobility. But terminal velocity is when you are no longer accelerating, you can't go any faster because of air drag. So that means if we come over here, we'll skip down to this question. Below the table, at terminal velocity, R equals what? Well, let's say we've got an object, right? The forces acting on the object are mg, and then there is a resistance R. Well, at terminal velocity, if you're no longer accelerating, you can think of this in terms of Newton's first law, right? An object is going to stay in motion unless acted upon by an unbalanced force. Well, in this scenario, we're just staying in motion. We're not accelerating. So you can then infer that we must not have unbalanced forces, meaning that the magnitude of R and mg must equal each other. So those two are going to balance out magnitude-wise. Obviously, the directions are opposite, but magnitude R equals mg at terminal velocity. So when we look at the equation at terminal velocity, ignore that negative there. We're not going to talk about direction. But mg is going to equal B times VT. We change R to mg, and V is now V sub T for terminal velocity. And we will look at the same thing over here. The equation for terminal velocity for type 2, instead of R, you just use an mg instead, and everything else stays virtually the same. Okay. Now there should also be a small t down there. Look at this, typos galore in my slides. 1/2 rho VT squared dA equals mg when you reach terminal velocity. Now, those are the two models we have for drag. We will talk about type 2 first because it has the more complex equation. We're going to go over those variables real quick. So what are the variables in type 2 drag? So first we have R, excuse me. Let's zoom in here so I can type a little, or write a little bit better. Okay, we have R equals any resistance force. Okay, this is not just air drag. Any resistance force can be shown as R, right? Next, we have the 1/2. We all know what to do with 1/2. Here we have rho. Okay, rho is a Greek letter commonly used for density. Okay. Density is rho. Now here, this would be the density of the medium that you are traveling through. Okay. And we'll talk about what that looks like for air drag in a second. Next, we have these two, well, I guess we have V first, right? V is velocity. We are all very familiar with velocity. Next is D and A, right? Now, D stands for drag coefficient. And a drag coefficient takes in many variables such as skin friction. Talk about that in a second. My goodness. Skin friction. And it also takes into account the shape of the object. And A takes into account the profile area. Now, excuse me, these two are very different, right? Profile area is kind of like if you were to take a picture of something and then just take the silhouette of that picture, right? So, for example, if you take my mugshot, right? Let's take it from the side. My profile, you can see, is the outline of my face, right? That's the profile area of my face. But that doesn't give you any definition about the concavity of my eyes, the how my cheekbone moves into my nose here. It doesn't actually give you information about the shape of the object. It just gives you the idea of what is the profile of the object as it comes perpendicular to your medium, right? As it meets that air head on. Drag coefficient actually takes into account the shape, right? So, for example, we have a soccer ball and a football, right? They have very similar profile areas with the exception of the strings on the football that cause a slight little ridge, right? But when you look at them head on, as they are thrown, they're both a ball, right? And a very similar size. Now, they fly very differently though, and that is not due to their profile area, that is due to their shape. The soccer ball is much easily kicked rather than thrown, and a football is much more easily thrown than kicked, especially given their respective sports, right? You wouldn't want to play soccer with a football. That would be nuts. And trying to play football with a soccer ball also would be kind of tough. Your quarterback wouldn't really be the star of the show at that point. So shape has a lot to do with it, right? Because the shape in a drag coefficient takes into account the cone-like nose of the football, where it's not just a circle. Actually, when it meets the air, it's really small, and then that gets bigger and bigger and bigger, allowing for more aerodynamic shape. There's also skin friction. Skin friction is really important. Really, when things are moving through air, their skin friction can have to do with maybe, for example, for a skydiver, loose articles of clothing. If you have skin tight suit, you have very little skin friction. But if you're like a baggy jacket or baggy pants and that's flapping in the wind, that could increase your skin friction. You also have rifling, right? Or just the spinning of an object. If you were to throw a football without spiraling, just throw it cone first, that football would kind of wobble through the air. But when it starts spinning, it actually cuts through the air. Similar to bullets, right? Back in the Revolutionary War, we didn't have rifling. We just had muskets that had a very smooth muzzle. And when the bullet would come out of that muzzle, it'd come out at a really fast velocity, but the bullet would kind of wobble through the air and it wasn't very accurate. But once we discovered rifling, right, then we invented that. Now the inside of a muzzle on a gun actually has grooves cut into the muzzle, into the gun, so that as the bullet travels, it doesn't just travel through a smooth muzzle, it actually starts spinning as it goes. So then the bullet is spinning as it goes, and it just kind of cuts through the air rather than wobble through the air. So that's what drag coefficients can take into account. It's just a general coefficient that can it can account for a lot of different variables that may have to do with an object moving through the air. So number two, the value of rho for air is 1.2754 kilograms per cubic meter at STP. What is STP? So STP, right? That is standard temperature and pressure. And the standard temperature and pressure are, so the temp would be 0 degrees Celsius, which is 32 degrees Fahrenheit, which is negative, no, not negative, Kelvin doesn't have negative. That is 273.15 Kelvin, right? Very cold temperatures. For pressure, this is not something that we've really gone over in class. When you move on in your physics career, you'll talk a lot more about pressure, especially when you get into thermodynamics. The pressure is standard at 100 kilopascals. Pascal is the standard unit for pressure. It can also be described as 1 bar of pressure, or it can be described as 0.987 atmospheres of pressure. Now, STP has changed over history. It used to be 1 atmosphere, but we moved away from that, I believe, in the 80s. But this is important because if you move away from that standard temperature and pressure, the density of the air is going to change. And hopefully the problem just gives you that, because it's not easy to find the density of air if you don't know the temperature and pressure of the environment. Now for number 3, compare the equation in number 1, the type 2 equation, R equals 1/2 rho v squared dA. Compare that to R equals BV, the type 1 drag. Excuse me, allergies. Compare that to the type 1 drag equation, R equals BV. What is the major difference between the two? So if we look at these two equations, so let me erase to get some room here, right? We have very different variables that we're looking at, right? We have several variables in type 2, right? We have 1/2 rho v squared dA. Then for type 1, we just have R equals BV. Now, you can see we have a lot of differences, and I'm not looking for all of the differences. I'm looking for what is the most important. So we have the absence of rho, D and A, and then there is this 1/2 that is also completely absent from the other equation. We do have V's in common. Now, if we look at the density, the drag coefficient in the profile area, that seems to be an obvious difference between these two, right? However, that's not what I want to focus on. I want to focus on the difference in velocity. If you notice, the difference here is the exponent, and that is the most important difference. Because if the velocity changes in a viscous fluid, it will directly linearly affect the resistance force. But if the velocity changes in air, then that exponentially affects the resistance that is caused by air drag. So the velocity actually plays a major role in air drag, but it doesn't play as heavy a role in viscous fluid. So that is a really important relationship to make between these two differences of type 1 and type 2 drag. And you could say that that is really the defining difference between the two, is that in air, velocity has a much bigger role than the other variables. Everything else just affects it by a factor of a linear relationship, just like in type 1 drag. But the velocity has this upper hand on everybody else. If the velocity changes, it affects the drag much more than if anything else were to change. So that is the major difference between those two. We also have this variable b, okay? And we'll talk about the units between these variables, but b here has to have some units. We'll look at the units for type 2 in a second. But for type 1, B is going to have some arbitrarily assigned units that don't really have a whole lot of meaning other than it is supposed to just be a variable that fits the scenario to match all of the given constants that are going on in that scenario. So next, let's talk about 6.3, the drag coefficient. Okay. So we have this table, 6.1, the terminal speed for various objects falling through air, right? These are sorted by mass. A skydiver has a mass of 75, cross-sectional area of 0.7 square meters, and a terminal velocity of 60 meters per second squared, which is really fast. Then we have baseball, golf ball, hailstone, and raindrop information, all sorted by mass. Then they have various cross-sectional areas and then terminal velocities. Now, would these objects all have the same drag coefficient? Well, we talked about drag coefficient, right? This, the shape of the object, not just the profile, but the shape of the object matters, as well as the skin friction of the object, right? So first, let's look at a baseball and a golf ball, right? They have very similar shapes, not very similar size, but very similar shape. However, the skin friction is different, right? A baseball has a relatively smooth surface compared to a golf ball. Golf ball has all of those little craters in it that actually affect the flight of the ball. And oh darn, I forgot the word, but the strings on the baseball, right? That also allows the pitcher to grip the ball and actually put spin on it. And that spin can also affect the drag coefficient, like we talked about with skin friction. Skin friction can either decrease the drag or it can actually change the trajectory of an object. In baseball, think of a curveball. Soccer, think about a corner kick or a penalty kick where you're trying to curve the ball. Or even in ping pong, you can make a ball do some crazy things in the air with skin friction in ping pong. So all of these objects are going to have a different drag coefficient, but part 1A wants us to calculate the drag coefficient of a baseball. So let's, where should we do our work? We're kind of out of space. I didn't give myself an extra area over here. So let's drop that size here and we'll zoom in. So we've got some given variables for a baseball, right? The mass of a baseball is given to us as 0.145 kilograms. the cross-sectional area is given to us as 4.2 times 10 to the negative third, and that is in square meters, right? Because we're talking about area. Then the terminal velocity, Vt, equals 43 meters per second. And if we want the drag coefficient, we're going to need an equation that has drag in it. 1/2 rho v squared dA, right? So we have the mass. Mass isn't even in that equation, so I don't know how helpful that is. We do have rho from our last slide, 1.2745. That is kilograms per cubic meter. If you want to remember the units for density, just remember the middle school equation. Density is mass times volume, which would be kilogram divided by meter cubed. So that's a pretty easy way to remember that. That's how I remember it anyway. So we've got mass, which isn't really there, area, we have velocity, we have rho, but we also don't have r. But notice that we have terminal velocity. So we actually need to modify our equation a little bit. Remember, we have a different equation for terminal velocity. mg equals 1/2 rho vt squared dA. So now we have m. We all know g by heart. We have rho, vt, and a. Now we can solve for that drag coefficient. So let's go ahead and move our things around. We've got 2 mg. Then we're going to divide by rho, vt squared, and a to get the drag coefficient of this baseball. Now let's put our numbers in. We've got 2 times 0.145 times 9.81 divided by, let's see, our density, which is 1.2745. Our velocity is 43, then square it. And then our area was, oh boy, 4.2 times 10 to the negative third. Now, let's put that in our calculator and see what we get. See if it's a usable number. All right, and we get 0.287. So this is your general size of a drag coefficient. Okay, it's usually a decimal. In my experience, usually a decimal. But we also don't. What are the units on this? What is the unit for a drag coefficient? So let's actually take this here and let's write out all of these units. So let's see, mass is in kilograms. Gravity is meters per second squared, right? 9.81 meters per second squared. Rho is a kilogram divided by meters cubed. Velocity is meters divided by seconds, but then we square that, and then we have area, which is meters squared. So we've got 4 meters on top, 3 meters on bottom. So let's get rid of those. Then we have, all we have left is this, oops, there we go. Kilogram meters per second squared divided by kilogram meter per second squared, which all just cancels. So D is unitless. What it is it is really a ratio, not a ratio, it is a constant that really sums up the relationship and the scenarios between the object and the air and the environment and how it's all interacting. So that is our answer, 0.287, given the data that we have here. That is the drag coefficient of a baseball. Now, let's discuss this. Would a skydiver change their drag coefficient? by changing their orientation. So let's look at this. The body's orientation. Well, the shape has a lot to do with it, right? So if you are spread eagle, you actually have a slower terminal velocity than if you were to go pencil dive, right? Now you think that has to do with profile area, but it also has to do with your shape, because when you're pencil diving, right, you're actually more aerodynamic. You don't have as much contact with the air, which has a lot to do with the shape, right? Not just the profile area, but the three-dimensional shape of the object. So you can actually change the drag coefficient just by changing your body's orientation. That pencil dive will make you go faster. If you need to slow down, you need to go spread eagle. Then changing their uniform. How could that uniform actually make a difference? Well, like we talked before, if you have skin tight uniform, you're not going to have as much skin friction. But say you have like a really baggy jacket and really baggy pants when you skydive, all that fluttering is actually going to slow you down, and it would be measurable that you could actually calculate how much that was affecting you. So actually changing your uniform can affect the drag coefficient value when skydiving. All right, last slide is type 1 drag. So R equals BV. So we've got a couple pictures here I want to talk about real quick. Here, if this is just an example of terminal velocity, right? You start out with velocity equals 0, acceleration equals g. But then eventually, you can see that those start spacing out more and more and more until eventually the velocity is terminal velocity, but then your acceleration is now hit 0. So this is your acceleration vector, and then this would be your velocity vector. And as you can see, the velocity vector hits a point where it just stops getting bigger, and the acceleration hits a point where it gets so small it's now 0. So that's kind of how we can envision terminal velocity there. Then over on this side, again, another way to envision terminal velocity. Here you've got a velocity vector with r smaller than mg, but as the velocity continues to increase, remember, as v increases, so does the resistance. But there will be a point where the resistance matches mg, and that will mean that the acceleration reaches 0 because of balanced forces. So that is especially true in R equals BV because of the linear relationship between the velocity and the resistance. So first, let's talk about B. What is B and its units? So B is this kind of messy combination of area, drag coefficient, density. So if we look at what it actually means, right? So resistance has the density of newtons, which is a kilogram meter per second squared, right? And then velocity has the units of meters per second. Well, if we solve for B, B is R divided by V, which means that B could equal a kilogram meter per second squared. You could say divided by meters per second. Sometimes it's easier to multiply by the reciprocal to show you that you can cancel the meters, cancel one of those seconds out. So it would give you kilogram divided by second. So kilogram per second. What does that even mean, right? You can also just say that B equals newtons divided by meters per second. That's also a valid unit, right? Not as simple, I think, as kilogram per second, but it has a little bit more meaning. Newtons per meters per second has a little bit more meaning than the other one. So number 2, derive an equation for type 1 drag at terminal velocity. So if we were to look at type 1 drag at terminal velocity, right? So if we've got to balance our forces here, what could we arrive at? So we've got R equals BV. But if we're at terminal velocity, remember that makes a couple assumptions. velocity goes to vt, and r equals mg in magnitude, not direction. So if we take those into account, all of a sudden we have mg equals bvt. That also means that you can also look at the terminal velocity, vt, as mg divided by b. That equation can come up and be very useful in your equations or in your problems as you're working through type 1 drag. All right, so that's type 1 and type 2 drag. Next time, we're going to go over the time constant, which is a very important variable in physics and engineering, and it has several different uses in the respective fields.